Okay, pressure. What pressure stands for is the amount of force that a gas exerts on a given unit of area. Mathematically, pressure is given by the force of the gas divided by the area to which that force is being exerted. And the units from the physics point of view are kilogram times meters per second square for force and meter square for area. So carrying on the division as depicted here shows us that the units of pressure from the physics point of view should be kilograms divided by meters over second square. And another way to kind of make this simple and just kind of collectively refer to those units without having to say them is to refer to them as a Pascal. And 1 Pascal is simply 1 kilogram over meter second square. Now, in order to get an idea of how big or small this unit of pressure is, we have to consider how much air there's present at sea level. It turns out to be the case that 10,339 kilograms worth of air are sitting on top of a square meter worth of area, going all the way from the surface of the Earth at sea level to the stratosphere itself. So we use the formula given above, pressure equals force over area, and we use the premise that force is the mass of an object or substance multiplied by the gravitational force. Then plugging in the values right here tells us that 10,339 kilograms multiplied by 9.8 meters per second square, aka the gravitational constant, all divided by 1 square meter, cancels out the meters, gives us the right units, kilograms per meter second square, and we end up with a value that is 101,325. This is in essence the conversion of what we call the atmosphere, because as it turns out to be the case, the Pascal is a very small, an inconveniently small unit of pressure. So instead of dealing with Pascal in chemistry, we deal with the atmosphere, and the two of them are simply stated the same value. They represent the pressure at sea level. All right, but most commonly we're going to refer to it as atmospheres. However, there's another unit of pressure that is just as important and just as well used in chemistry, and it's called the millimeters of mercury. Now, the name of the unit itself sounds rather silly, like millimeters of mercury. What? It doesn't even sound like pressure. But the idea actually comes down from the use of all barometers, like the ones that you see right here. These are all barometers that contain mercury. These are, pretty old. They're actually part of a museum at the National Institutes of Standard and Technology. But as you can see, most of them have a U tube type of shape. And as depicted here on the diagram, it is via this U tube that we determine how much pressure there is on the outside of this tube compared to the material present inside the tube. So basically what you do is you place a substance in here, a liquid substance. And because atmospheric pressure is actually relatively high pressure, you need the substance here to have a relatively high density. It turns out to be the case that the substance that does the trick for this type of setup is mercury, because mercury, being a liquid and being a metal, a heavy metal at that, has a really high density, a density of 13.59 grams per cubic centimeter, or grams per ml. And so what happens is that you have to take this tube and have it fully evacuated. So this head space right here has no air whatsoever. And the same thing goes for this headspace right here. And this is close to the outside atmosphere. So then what you do is to determine the pressure is you open the stopcock right here and you let air from the outside, from the atmosphere at sea level, come in. And what happens is that the gas, due to its low solubility in liquids, ends up pushing the liquid upward. So you start initially at a point where the liquid on either side of the U-tube is at the same level, but by the time the force of the air comes in, it pushes it up the column. And here you literally measure in millimeters how far up the column the mercury traveled from the initial point it started at. And it turns out to be the case that at sea level, with that amount of pressure, you can raise the mercury by 760 millimeters. And so that turns out to be the unit of pressure that we use. And another way to look at it from the physics point of view is that force over area is mass times the gravitational constant over A, but mass can be also obtained by multiplying the volume with the density of the liquid. So if we apply all of this, oh, and also if we deconvolute the volume by being area times height, the areas cancel out and you end up with density of the liquid times the gravitational constant times the height the liquid travel up the U-tube, equating to the pressure of this thing. And so that's a way in which you can find out exactly what that is. And I'm going to show you in a second that ends up being exactly what we expect to be in pascals. But most importantly, what I want to point out is that 1 atmosphere equals 760 millimeters of mercury. And even though the unit is kind of weird and incorporates the symbol of the element within it, this is actually a unit of pressure because it has literally to do with that. You know, how much pressure is the gas exerting on the liquid mercury in order to raise it by 760 millimeters mercury. So remember, this is a conversion factor. In addition, a little bit redundant, but often used nonetheless, is the unit of torr. Now this is in honor of one of the early scientists that dealt with gases, Torricelli. And technically 1 Torricelli equals 1 millimeter of mercury, or to put it differently, 1 atmosphere equals 760 torr. I would recommend that you remember these two conversion factors. I will not be providing you with them, and I will expect you to remember them. 1 atmosphere equals 760 millimeters of mercury, which equals 760 torr. All right, now to kind of show you concretely that this formula, density times the gravitational constant times the height that the liquid travel equals the pressure, we're going to input all the stuff that we have here. Okay, so we have first of all density of the mercury is 13.59 grams per cubic centimeter. So we input the 13.59 grams on top, the 1 centimeter on the 1 cubic centimeter at the bottom. We multiply by the gravitational constant, 9.8 meters over 1 second square, and we multiply by the 760 millimeters of mercury, right? Which is the 760 millimeters, which is the height the mercury travel. All right, now, so all that needs to happen here is that we need to do a few conversions because we need everything to be in meters and we need everything to be in kilograms. So we want to take care of the centimeters first. We have 1 cubic centimeter on the bottom. So we need to use 100 centimeters on top, equaling 1 meter. And because this is cubic, we need to cube this entire term so that the units will cancel out. All right, and when you distribute the cube, the 10 to the second, which is the 100, becomes 10 to the 6th. All the units now are cubed. So your cubic centimeters will cancel out. And now you have cubic meters, so that's perfect. Now we need to take care of the millimeters. And for that, since we have millimeters on top, we place 1,000 millimeters on the bottom and 1 meter on top. Now everything is in meters, so that's perfect. The last thing to take care of is the grams. We need that to be in kilograms. So we divide by 1,000 grams and multiply by 1 kilogram in order for all the units to cancel out. And notice that all that's going to remain is going to be kilogram divided by meter divided by second square. When you multiply all of these numbers together, 13.59 times 9.8 times 760 times 10 to the 6th divided by 1,000 divided by another 1,000, you end up finding out that this value is 101.325 kilograms per meter second square. In other words, the pressure at sea level in pascals. All right, so pretty much that presents all the conversion factors that I want to show you. Namely that 1 atmosphere equals 101,325 pascals. So you can have either of these two fractions for your conversions. That 760 millimeters of mercury equals 1 atmosphere. So you could have either of these two things as your conversions. And the same thing goes for torr. You could have either of these two fractions as your conversions. And this set of conversions you need to be pretty good at doing. For the pascals, I will probably provide you with that number, but as you'll find out in later lectures, it might be kind of convenient to remember this number as well. But the ones that I definitely want you to remember is the 1 atmosphere equals 760 millimeters mercury and the 1 atmosphere equals 760 torr. Okay? The next lecture, we'll talk about the 2D gas laws.